We've been messing around with wind and solar for many years, so we thought it appropriate to do this short video describing the various parts of such a system. The home generation of electricity is important for many factors, primarily to reduce your utility bill and your carbon footprint, but also if lots of people were generating usable power and feeding it into the grid, then it's a way of decentralizing electricity generation, and so increasing energy security and reducing CO2. With the advent of modern grid tie inverters and the feed-in tariff, this is increasingly easy and makes more sense. Here we are in Lincolnshire, bright January morning. There's no wind, which of course means the turbine's not going round, but it does mean it's alright for filming, so the wind doesn't get in the microphone. Here we have a downwind machine, downwind turbine, on a 15-metre tower. The height of the tower is important, so it takes the turbine out of any local turbulence created by buildings, trees and what have you. Small wind turbines are designed around two basic formats, downwind and upwind. The downwind machine is where the blades are downwind of the tower, and the upwind the opposite. On a downwind machine, the blade overspeed needs to be controlled, and on this one there is vary pitch to change the angle of the blades. On an upwind machine, the tail that directs the turbine blades into the wind is designed to fold and therefore reduce overspeed in high winds. Overspeed is a particular problem of turbines, whereas you want the power, but there comes a point where mechanical damage could occur. Here's the turbine going in a reasonable wind. It may not look to you as it's going round fast, but it is. And you can hear the vary pitch spilling the wind. This is a small upwind turbine of about 1.8 metres in diameter. It costs less than 10% of the big turbine. Lightweight, easy to install. This is actually a 24 volt system. This turbine will give 1 kilowatt. It has 5 blades, which means that it's very stable, and the tail folds, and in high winds of 50 mile an hour, 40 mile an hour, the tail does fold up and the rotor is then edge onto the wind. They don't look like they're going round very fast, but actually they are, just to do with the effect of the camera. Here we see the large armoured cables that bring the power from the turbine and off to either the grid tie or the battery shed. There are 3 cores in these cables, taking the 3-phase AC from the turbine. The cables need to be large enough to avoid volt drop. Volt drop is where the cables are not large enough to allow the current to pass freely, and so therefore power is lost in the cables. The 3-phase AC from the turbine comes into the rectifier. The rectifier is this big black finny type thing. They don't always look like this, but this is one out of an industrial MIG welder. The 3-phase comes in the blue, red and yellow, and because this is a battery system, that 3-phase is a nominal 50 volts. The rectifier, out of the rectifier then comes the DC, positive and negative. It's an exceptionally windy day. I just thought I'd bring the camera in here to show you the ammeter, how it fluctuates. See there, it's about 20 amps, down to 10, when the wind gets up it'll go above 30. If it's charging at 20 amps on a 48 volt system, let's call it a nominal 50 volts, 20 times 50, 2 5's 10, that's 1000 watts. That's a kilowatt. So when it gets to 30, it's a kilowatt and a half. I'm going to do a separate video about the correlation between amps and volts and the various calculations behind that. This is called Ohm's Law. Look at the other video if you're not sure about this. Here we see a solar array made up of 4 12-volt panels. In this case these are wired in series to give 48 volts, and this is suitable either feed into a 48 volt battery system or a small solar grid tie. These panels could be wired in different ways to give either 12 or 24 volts, depending on the battery or grid tie working voltage. System voltage is important for many diverse reasons, and the reasons for this are covered in great depth in my book Wind and Solar Electricity. This array is designed to track the sun, and this is important as the panels work most efficiently when facing directly towards the sun or 15 degrees either way. For this latitude, i.e. in Britain, there's a marked difference in solar radiation between winter and summer, and for this reason the tracking can give up to 50% greater output in summer, but is only a marginal benefit in the depths of winter. On a 24 volt system you only need 2 12 volt panels in series to make up enough panels to charge at system voltage. The array is mounted on a pole, and this is for several reasons. The first one being just the reduction of potential damage, lawn mowers and that sort of thing. The second one is to reduce the potential of shade from surrounding trees, bushes and buildings. Being on a pole also facilitates the tracking mechanism, makes it very easy to fit the tracking. Also, because of the difference in the height of the sun between summer and winter, the angle of the panel must be changed at several points throughout the year, and mounting it on a pole means that it's quite easy to change that angle. This is a screw jack that drives the tracking. Same sort of thing as used on satellite receiver dishes. Beyond the benefits of tracking, it's important to realise that if any part of one of these panels was shaded, because they're all wired in series, then that particular bit of shading on one panel would affect the output of the whole array. Because of this localized shading effect, it's very important to choose the location of the panels carefully and watch over a period of time where the shade comes at various parts of the day. Here's the board where the power from one of the solar arrays comes into the battery shed. As you can see, the amp meter is showing about 5 amps. So it's a reasonably bright day, but the sun's quite low in the sky. 5 amps at a nominal 50 volts, 5 5's 25, so therefore we're charging about 250 watts. To the left of the amp meter there's a relay and a small circuit board. These two items control the tracking of one of the arrays. The relay is a forward and reversing relay, so that at the end of the day, say 8 o'clock at night, the panel or the array starts tracking backwards, so it's ready facing the sun in the morning. And the small piece of circuitry is an interval timer. This is set to run at about 15 seconds every half an hour. This is the inverter. It takes the battery power at 48 volts in this case and changes it into mains power at a true sine wave. In this case, this inverter is also a UPS inverter, in so much as when the batteries get low, then it will automatically change over to mains power. The parameters for this function are fully adjustable. This is the battery pack. In this case there are 24 600 amp hour cells wired in series to produce a 48 volt battery pack. That means each cell is a nominal 2 volts. If you wanted a 24 volt battery pack, of course, you would only have 12 of these cells. There is a 1 litre jug shown on the battery to give you some sort of scale. As with the power cables that come from the turbines and the solar panels, the cables that are attached round the batteries have to be very large to avoid a volt drop. The calculations for volt drop are included in the book, an image of which will be shown at the end of this video. Here we see the backup battery charger. In this case it's quite large because it's a forklift battery charger, but you can set the current at different levels. It's important to have some form of charging beyond the wind and solar generation. Very important not to have the batteries sat flat, so therefore even if you're on a off-grid system, you'll need a generator to run a charger like this. It's very bad news to have the batteries standing flat and you have no power. As the power in a lead acid battery is used up, the strength of the acid is reduced and lead sulfate is created on the battery plates. This lead sulfate can cause damage to the battery plates if the battery is left discharged for any length of time. This is not the only reason for not leaving batteries in a discharged state. There is also the fact that further damage will be caused if you try to take further power from the system. And also, when the acid is very weak, it can freeze in bad winter weather. This, of course, creates further irreparable damage. For a battery pack to act as a reliable power source, then it must be kept fairly well charged most of the time and never discharged below 50% of its rated capacity. As a rule of thumb, I never discharge below a specific gravity reading of 1200. And of course, in this photo or this video, you can see a hydrometer on the battery pack. A hydrometer is used for measuring the specific gravity of the acid. There's shed loads more on this subject in the book.